In this lecture, we will be looking at a type of time series called a moving average of order 1 time series or processes. So moving average of order 1 process, the idea is that the process yt is a weighted average of its past white noise terms plus a new white noise term. So our formal definition is as follows. Suppose we have a white noise process, mean 0, variance sigma sub epsilon squared. We say our time series y1, y2, y3, so on and so forth, is an MA1 or a moving average 1 process if for some constant parameters mu and theta, we have this defining equation 1 here. Specifically, yt minus mu is equal to epsilon t minus theta times epsilon t minus 1 for all t. Mu is our mean of the process. Theta is the weight for the previous noise term. The idea here is that this time series, we're trying to give it some memory. And if you've watched a lecture on the AR1 process, for an AR1, we have that the way that yt differs from its mean is a piece of how it differed from its mean yesterday plus a new noise term. So let's think of time as in days. It can be at any time scale, but for illustration's sake, we'll think of it in days. So again, how did the time series differ from its mean today? You remember, think of it like a percentage of how you differed from the mean yesterday, plus a noise term to represent new information. Here we said, if we want to build some memory into our time series, let's allow it to remember a previous value of itself. Well, there's another way we can build in memory, and it is this way here. The difference is instead of letting yt remember something about itself, it's remembering a piece of the noise term from the prior day. So this is different than the autoregressive case, remembering a piece of itself, or remembering a piece of that previous noise term. So yt differs from its mean today with some new information, and then you add, or rather subtract, some percentage of yesterday's noise term. You want to be careful when you use different references. Some books will have a plus theta here, some will have a minus theta. That's also true for software. So if you're programming dealing with time series and you're actually doing some sort of routine where you're using moving average series, you have to pay attention to documentation for code and packages that are already written to make sure that you actually have the sign correct here. For this type of process, yt, it's weakly stationary for any values of the parameters mu or theta. And again, as we mentioned, epsilon t represents the effect of new information at time t. If we look at properties, the first property is to deal with its expectation. So if we take the expectation of yt, so we bring this mu to the right-hand side, then linearity of expectation tells us this is the expectation of mu plus the expectation of epsilon t minus theta times the expectation of epsilon t minus 1. And we know, first of all, mu is a constant. So the expectation of a constant is mu. The epsilon t, recall, are white noise terms which have mean 0. So this means both this expectation and this expectation are 0. And we in fact do confirm that the mean of an MA1 process is mu. To compute the variance, this takes a bit more work. So by definition, the variance of yt is the expectation of yt squared minus the square of the expectation of yt. And so we can work out this calculation. We have this second term, expectation of yt. This is mu. So we have a minus mu squared, and here we replace the yt with mu plus epsilon t minus theta epsilon t minus 1 from the defining equation for the MA1. Now we need square this term out inside the expectation. So first we multiply mu by each term. So we get mu squared plus mu epsilon t minus mu theta epsilon t minus 1. Then we multiply epsilon t by each of the three terms, and we obtain mu epsilon t squared, and then minus theta epsilon t minus 1. And finally, we multiply this last term, negative theta epsilon t minus 1, by each of the three terms in the parentheses, and we get mu negative mu theta epsilon t minus 1 minus theta epsilon t minus 1 plus theta squared epsilon t minus 1 squared minus mu squared. And we see there is one quick, well, we now use linearity of expectation, and also the fact that some of these terms combine. So we see we have a mu epsilon t and a mu epsilon t here. We have a negative theta epsilon t minus 1 here and here. And we also have this minus mu theta epsilon t minus 1, minus mu theta epsilon t minus 1 here. So we see a few of these do in fact combine. So we have the expectation of mu squared, and again we're using linearity of expectation. So expectation of the sum is the sum of the expectations. Then we have this next term, so we have two of these. So plus 2 mu expectation of epsilon t. Then we have two of these terms. So we have minus 2 mu theta expectation of epsilon t minus 1. We have our epsilon t squared. Then we have these two terms here. And so we have minus 2 theta expectation of epsilon t minus 1. And finally, the last term, plus theta squared expectation epsilon t minus 1 squared. And at the end, minus mu squared. Now, simplifying some of these, we see here the expectation of a constant is, of course, a constant. And we see that this mu squared will pair with this negative mu squared. And so those will cancel. And now we can make some conclusions on these terms here. One in particular, notice because the epsilon t sequence these terms are uncorrelated because they're a white noise. This means that expectation can be written as the product of the expectations. And again, that is because the epsilon t and epsilon t minus 1 term, these are uncorrelated. So, summing this all up on our next slide, we have here, notice this mu actually had canceled with this minus mu squared. And now we note that we know many of these expectations. So coming back to our epsilons, remember that our epsilon t's are white noise with mean 0 and variance sigma epsilon squared. Because we have a mean 0, every one of these expectations of an epsilon t or an epsilon t minus 1 are 0. But since the expectation of epsilon t is 0, right, remember our variance definition. So the variance of our white noise term would be the expectation of epsilon t squared minus the expectation of epsilon t itself squared. But that second term is 0 because epsilon t is mean 0. We know epsilon t, the variance, has to be sigma epsilon squared. So this tells us the expectation of epsilon t square is in fact sigma epsilon square. So we can now go in and make that change, and here we have sigma epsilon square, and here we have sigma epsilon square. So simplifying this, many of these terms have dropped out. We're only left with these two remaining terms. So we have sigma sub epsilon square plus theta square times sigma sub epsilon square, or sigma sub epsilon square times the quantity 1 plus theta square. And this is the variance of our AR1. And to sum up, we have it expressed here. Our AR1 has mean mu and variance quantity 1 plus theta square times sigma epsilon square. Now notice these are both constant, and there are no conditions on mu. There are no conditions on theta, which tell us that yt is weakly stationary. For all mu and theta. There are no conditions. And remember, the condition for the definition of weak stationarity is that you have a fixed mean of your process and a fixed variance of your process, which we have explicitly here. Now we want to talk about the autocovariance and the autocorrelation structure. And this is a very interesting property for a moving average 1 process, which we'll see extend to a more general moving average process. But our autocovariance function for lag h, and remember the idea of autocovariance. Autocovariance, you take on your time axis, you look at, say, yt, and then you advance an increment of h in time. And we're looking at the dependency, in particular the covariance, between these two terms. And this autocovariance function will be a function of h, which is the lag, or the amount of time in between these two observations of your time series or the values of your process. So by definition, the autocovariance for lag h is the covariance between yt and yt plus h. And we have 3 different cases. So the first case, notice this is actually the variance of the process. So recall that the variance of a time series is the same thing as the autocovariance with at lag 0. So if you plug in h equals 0, you have nothing more than the covariance of yt and yt, which is the same thing as the variance of yt. At lag 1, so notice here, this is what we computed on the previous slides. At lag 1, our autocovariance is minus theta times the variance of the white noise. And for all lags beyond 1, our autocovariance is 0. And so this below is an example of an autocovariance function. This is actually flat here. We see, in this case, this was a case for a moving average 1 process where we had theta is minus 1/2 and mu is 0, and we see we have a autocovariance of about 0.8. That's the variance of the process, right? That's your autocovariance at lag 0. Down here is our h-axis. And then we see a covariance of about 0.33 at lag 1, and autocovariance drops to 0 at future lags, or lags bigger than 1. You can derive this in a similar manner as to how we just computed the variance by using this defining equation and plugging in, moving the mu to the right and plugging that in here, and then rewriting this equation with t replaced by t plus h. And you use your defining equation for covariance, right? We know covariance would be the expectation of yt times yt plus h minus expectation of yt times expectation of yt plus h. And use this equation to plug in here and use your rules for expectation and the properties of the white noise epsilon t to simplify to this expression. Again, very similar to the calculation that we just did. But it's important to recognize that it's after just one lag, the autocovariance drops to 0. The reason for that is when you look at this defining equation, you can see yt, how it differs from its mean, has 2 random variables on the right-hand side. One is this new epsilon t. The other is the previous epsilon t minus 1. But epsilon t and epsilon t minus 1 are memoryless. Remember, these two things are uncorrelated with each other, but they're also uncorrelated with earlier noise terms, epsilon t minus 2, epsilon t minus 3. They're also uncorrelated with earlier values of yt, like yt minus 2 or yt minus 3. The point is, on the right-hand side of this expression, there is no memory of anything that has happened prior, or 2 steps prior, or 3 steps prior to time t. Because of that, you cannot get any autocorrelation with a lag bigger than 1 in size. Now that we have our autocovariance function, we can look at our autocorrelation function. And remember, to get autocorrelation, we simply take the autocovariance function and divide it by the variance of the process, or the autocovariance at lag 0. Sigma epsilon squared times the quantity 1 plus theta squared. So we use that here to get that rho of h is gamma of h over gamma of 0. And of course, when we divide gamma of 0 by itself, we get 1. And then when we divide gamma of 1 by this variance, you see the sigma epsilon squareds will cancel. And for the lag 1 term, we're left with negative theta over 1 plus theta squared. And we have a 0 correlation for lags in size larger than 1. And we see our autocorrelation function illustrated here for one particular case. Working through some examples to see what these processes actually look like, we start here with an MA1 mean 0 with theta is negative 0.9. So you can see from our MA1 equation, we have yt equals the new noise term plus 90% of the previous noise term. Here we have one trajectory for this process, and here we have the autocorrelation function. You see autocorrelation at lag 0 is 1, autocorrelation at lag 1 is about a half, and then it drops to 0 after that. And you can see a little bit of structure in here, and the key thing to remember is that you have this memory in this process of 90% of the previous noise term. And so that causes a little bit of kind of clumping. You can see some of this clumping happening here in these different cases. And this will become a little bit clearer as we work through more examples where theta works its way up to 0. So let's look at the case where instead of negative 0.9, it's minus 0.75. And you see you have a similar effect. It looks a little bit more like a white noise. And actually the autocorrelation structure is about the same as it is in the negative 0.9. But you still see some of this clustering clumping because of this memory on the previous noise term. If we go to negative 1/2 for theta, you see you still have this kind of clustering effect, but again it's looking noisier and noisier. Our autocorrelation function drops a bit at lag 1 to 0.4. If theta is negative 0.25, then again this is looking more and more like a white noise, and we see our autocorrelation now drops to about 0.2 at lag 1. And then when we go theta equals negative 0.1, you see things are looking very noisy, and it's because we have this only 10% memory for the previous noise term. Our autocorrelation is actually down to, you see, about 0.1 at lag 1. And then if you reduce, or if you increase theta all the way to 0, you actually get a white noise where you have 0 or autocorrelation at lag 1. But it can be a little bit easier to see if we step through this more quickly. To get a feel for these, let's actually look and see how the trajectory for the process changes as we decrease from theta from 0 down to negative 0.9. So here we have our white noise process when theta is 0. theta is minus 0.1. You can see that a little bit of that memory showing up in there, but it still looks pretty close to the white noise. Theta is negative 0.25. Theta is negative 0.5. And then theta is negative 0.9. And the key thing is you can see how much this plot differs from the white noise plot. So this gives us an idea of what these moving average of lag 1 processes look like. They are going to be part of a bigger picture in our work with time series. So the next step will be to look at MAQ processes, where we give a lag beyond just one time step.